All right, so I guess first thing, we have what's it called? We have two attendance quizzes this week because I'm running out of weeks, so I gotta get these bad boys in. One is literally you have to look at four different memes and pick the one that has a double bond in it. So like at least the first one's not hard. So again, there's one question. You have an hour. You have like all week to get around to doing both of them. So if you have 2 minutes, you should probably do them. All right, so what am I gonna get for the first one? Gonna get a ketone, and it's symmetrical, so it doesn't matter which side you put it on. You are good. What am I gonna get for the second one? Get an aldehyde, right? Hydroboration puts the oxygen on the least substituted carbon. Right, just to help count. Carbon here, here is there. So what am I gonna get for the first one? You had two bromines, right? Because I'm adding Br2, I'm adding a bromine to each side, but I have one equivalent of Br2. So that means I only have enough Br2 to react with one of the two pi bonds. So I'm still going to have a double bond left in my product. So what about the second one? Yep. So I end up with the tetrachloride. I can actually get that bond there. There you go.
I was asked here why I get two chlorines on the top and two chlorines on the bottom.
Well, top and bottom kind of weird nomenclature, but right. So I add one of the first equivalent makes the dichloro alkene, and then the second equivalent reacts with that double bond to put on two more chlorines. So when you have two equivalents, you have enough reagent to react with both pi bonds in the alkyne to give you four chlorines added total and no double bonds at the end. So what am I going to get for the first one? Yep. So you're just going to end up with, I've got 1, 2, 3, 4, 5, 6 carbons. So I'm just going to end up with hexane. And then what am I going to do for the second one? What am I going to do with Lindlar's catalyst? Yeah, so you'll go from a triple bond to a double bond. And will that double bond be cis or trans? Cis. Yes. So I drew it like this in the early class, and they're like, does it matter how you draw the 3 carbons after the double bond? And the answer is no, right? Because it's just a different Newman projection, so it doesn't matter how you draw it, it's still going to be the same molecule. So as long as there's 3 carbons, the last one's a little sketch, but as long as there's 3 carbons, you are good. There you go. You're good. So it doesn't really matter how they're arranged. What really matters is that you clearly show that you have the cis double bond. So we left off on doing a dissolving metal type reduction, so sodium ammonia. And an alkyne makes a trans double bond. So Lin-Large makes cis, this makes trans. So when you have sodium and you dissolve it in ammonia, basically you make a bunch of like sodium radicals, which can then react with your alkyne. Gotta do it this way to do it better. So it's gonna go to the carbon. These electrons are gonna go meet it. And so this guy right here is a vinyl radical. So the carbon that's on a double bond that has a radical on it. This overall, this is a radical anion, right? Because it has both a radical and it has a carbanion. It has a negative charge. So when you look at a carbon metal bond, anytime you see a carbon metal bond, you can, in your head or on your page, break that bond in half and say, hey, the metal side, the sodium in this case side, that's going to be positive, right? And now the carbon that that metal is bonded to, that's going to be negative, right? So the carbon that has the sodium on it is the anion part of the radical anion, right? It has a radical and it has an anion, right? So now this radical anion, I'm going to have to redraw it on the next page again, can react with ammonia. Let's go to radical anion. And that anion can grab a hydrogen off of ammonia. Now, what's unique about vinyl radicals is the cis-trans geometry of the double bond is not fixed. So this radical can, basically that methyl group can move from the from the trans conformation to the cis, then goes back and forth, right? It's going to settle out on being the double bond geometry that is most stable. So right, the trans double bond is more stable, so it's going to spend more of its time. It's going to end up being that isomer. I drew it all the structures were all the trans, but you could have easily drawn it as the cis. But at the end, it like equilibrates to the more stable version, which is the trans version. So this trans again, I'm going to redraw it so I have space. This trans vinyl radical can react with sodium radical again. They'll come together. And make an anion again. Once it makes the anion, the double bond geometry is locked. So when it's the radical, that methyl group can flip back and forth, back and forth, back and forth, and eventually it will all end up being the trans isomer. And then when the sodium adds, you've locked that double bond geometry in. And now again, this can react with another ammonia, which I'm going to need some space. So this always gives us the trans double bond. So we can use Lindlars to make the cis, and we can use sodium ammonia or lithium ammonia to make the trans. Seem reasonable? Not too bad. So I have taught you how to do reactions with alkenes. I have taught you how to do reactions with alkynes. I've not shown you how to make either, right? Like, where does an alkene come from? When a mommy molecule and a daddy molecule love each other very much. No, so I'm going to teach you now how you make alkenes and alkynes, right? So synthesis of alkenes. We have two ways to make alkenes. The first is dehydrohalogenation. So you remove HX from a molecule. So if you remember hydrohalogenation, right, where you have an alkene and you add HX and you make an alkyl halide, right, a thing that has you've added a hydrogen next to. Dehydrohalogenation is just that reaction in reverse. All right, so we're going back to what we started with in that reaction. All right, so you can go from alkene to thing that has a halide in it, or you can go from thing that has a halide in it back to the alkene, which is what dehydrohalogenation is. The other way we can do this is dehydration. All right, you remove water from a molecule. Again, right, just like we could take water and sulfuric acid and do a hydration, right, to add water to our molecule. Dehydration is that reaction in reverse. So let's go into a little bit more. Let's do some actual examples of these as opposed to just like this, right? So for dehydrogenation, you have your halide. You need to add a base, and that will make your double bond. The bases that we're going to use are usually hydroxide bases or alkoxide bases. You need a metal, right? You can't just go grab a bottle of hydroxide off the shelf, right? You can't just have OH minus. It has to have some positively charged thing to balance it out, right? So whatever metal we have to put with our oxygen is just there to be the positive charge to balance out the negative charge of the O, but it's not going to impact how the reaction proceeds, right? Again, we can do the same thing. We can say, hey, we split this in half. The metal side is plus, and whatever atom is bonded to the metal is negative, right? So your oxygen is still an O minus. It just has an Na plus chilling out beside it. Right? Counterion doesn't matter. You're just going to remove a hydrogen and make a double bond. So how do we know where the double bond goes? Right? For this top one, it doesn't matter. This or this are the exact same thing. Right? But how do we know where the double bond goes? Where is it going to end up? So the way these reactions work, we're going to look at the mechanism real quick, and then that's going to kind of help explain what's going to happen. Right? So we have our simple example here. Make our double bond. Right? The mechanism is literally the shortest thing it could be. Your hydroxide, whatever your base is, grabs the hydrogen. The electrons in the carbon-hydrogen bond fall down to make a double bond and push the bromine out, or whatever your halide is, to make your double bond. So this all happens in one step, right? So you always have to make your double bond to the carbon beside where the halogen is, right? So the way we can look at these is we say, all right, here's our halide. So the alpha carbon is bonded to the halide. And then we have the beta carbons. Right. So your beta carbons are bonded to the alpha carbon, and they have the hydrogens that you can remove to make a double bond. Right here, I have two different beta carbons, right? If I were to remove the hydrogen from beta 1, right, so try to remove, making blue, remove from beta 2, I wouldn't make that, that's the thing I just made. Right, as if I remove the hydrogen from beta 2, I get two different products, right? So how do I know which one of these two products I'm going to make? Right? And we can predict which product we're going to make from Zaitsev's rule. So if you remember when we talked about hydrogenations, we said that tetrasubstituted double bonds are the hardest to hydrogenate because they're most stable, right? Then trisubstituted, then disubstituted, then monosubstituted. So the more substituents, the more carbons you have on your double bond, the more stable the double bond is. So every time you do one of these reactions, right, you do a dehydrohalogenation, your goal is to make the most substituted double bonds you can. And the way you do that is you take the hydrogen, or you take a hydrogen from the beta carbon that has the least other hydrogens with it, right? That's the most substituted beta carbon, and that's going to lead to the most substituted double bond you can make. So, right, again, my super easy one that you already know the answer to, right? I don't know why, I really lost the ability to write there. If alpha, beta 1, beta 2, beta 1 has 3 hydrogens on it, beta 2 has 2 hydrogens on it, beta 2 has less hydrogens than beta 1. That's where your double bond goes. So this works for pretty much any example. Right? You're just going to do the same thing over and over and over again. You're going to find your alpha, you're going to find your beta, and your beta. Right? You're going to say, okay, beta 1 has 1 hydrogen, beta 2 has 2 hydrogens, 1 is less than 2. Thank you, Sesame Street. And you're going to make your double bond. Right? So if you, every time you go to make one of these double bonds, if you find your alpha and your betas and count the hydrogens, you're going to make the right double bond every single time. You can have a max of 3 beta carbons. Right? So where am I going to make my double bond to? Beta 1, beta 2, or beta 3? Beta carbon 1 because it has one hydrogen. I keep forgetting to change off of Forge. Right? Because there's one hydrogen, two hydrogens, three hydrogens. Convenient how I did that. All right. So your general rule of thumb, right? Right. So your double bond has got to be formed between your alpha and your beta carbon, right? So if you go to like put something in your double bonds like a million miles from where the halide was, stop. Something has gone horribly wrong, right? So you're always looking to identify your alpha carbons and your beta carbons and then count up the hydrogens, right? So for dehydration, it works pretty much the same way according to the Zaitsev rule. You're going to want to always make your most substituted double bond. The mechanism is different. Right, so you have an alcohol and you have acid and a triangle. When you see a triangle in like a reaction or in like a set of conditions, the triangle stands for that you're heating or just generally refluxing the reaction. And that will remove your double bond. And again, you're always going to make the most substituted double bond that you can. So there are two acids that do this really well. You have H2SO4 and heat. And it's going to make a double bond. Or you can use phosphoric acid, which is H3PO4. Right? And you can effectively do the same kind of thing that you did with your halide. You could say, hey, the carbon that has the alcohol, I can just treat that as the alpha carbon because that has the group that's going to go away when I make my double bond, right? And then I can have beta 1, beta 2, beta 3, right? Say, okay, which one has the least number of hydrogens? Beta 1. So I'm going to make my double bond there. Something that holds true for both of these reactions, right, is let's say you have a situation where you have it's really good. Here's my alpha carbon, beta 1 and beta 2, right? You have to have a hydrogen to remove from your beta carbon. So here, beta 1 has no hydrogen, right? So to do an elimination, I have to have a hydrogen to remove. So I can't make a double bond. Oh, and there's beta 3. Sorry, buddy. And there's beta 3. He's like, damn, no one loves me. Just out here in the cold, just chilling, hoping someone notices me, right? So beta 1 has no hydrogens, so I can't make a double bond to it, right? So I only have to look at beta 2 and beta 3. Beta 2 has less hydrogens than beta 3. So my product is going to be, we're not going to worry about the E and Z on the double bonds just yet. That's a problem for like 2 weeks from now, you or something. You now just needs to make a double bond. All right. Same thing holds true for dehydrohalogenation, right? If you have this, right? Here's your alpha, beta 1 and beta 2, right? Your beta 1 has no hydrogens, right? There's no hydrogen for the base to go grab. So I can't make my double bond to beta 1. So you have to do it that way. If you draw 5 bonds to carbon, leave. Get out. You're done. We're like 2/3 of the way through the semester. You shouldn't be doing this to me anymore. It hurts too much. The pain is too real. Right? So that's another thing, right? Is if you go to do that, if you go to make your double bond to beta 1, the product looks real dumb. And you should be like, oh yeah, I can't do that. It makes me sad. So it'll be fine. So how does dehydration work? So we've seen this kind of first step before, right? When you have an alcohol or water and sulfuric acid around, what's going to happen is you're going to protonate that alcohol. Now I have a water molecule effectively hanging off of my molecule, right? So now the oxygen can take its electrons back, break the carbon-oxygen bond, make a carbocation, plus make water. Then we could use that water or some other base in solution to grab this hydrogen and have it give its electrons to make a double bond to fill that carbocation. So then we get our double bond plus H3O plus. So since we go through carbocation, rearrangements can occur. This week, you doesn't have to worry about that. 2 weeks from now, you can deal with that then. Right now, it'll be chill. So far, so good. Not too bad. Right? So again, you're going to try to identify your alpha carbon, the carbon that has the thing that's leaving. For dehydrohalogenation, that's going to be a halide. For dehydration, that's going to be OH. Identify your beta carbons, and then pick the beta carbon that has the least number of hydrogens and make your double bond there. I made a crack about Sesame Street in the early class, and we have one student who's from Germany, and I was like, I don't know, German Sesame Street, and he was like, it kind of sucked. I'm like, I can only imagine that like you guys just watched like Good Morning Berlin and like we would now count 1, 2, and they were just like counting. And he's like, we have a game show where someone goes into a small room and messes it up, and then someone has to come in behind them and then put everything back in the correct place. I'm like, you have a game show where people just clean up after like children? Like that sounds awful. Like, what are we doing tonight? Oh, we are watching Cleaning the House. Yay! Oh God, this is awful. All right. So I've shown you how to make alkenes. Now I'm going to show you how to make alkynes. One way to do it is through dehydrohalogenation of vicinal dibromides. So you have 2 bromines on adjacent carbons. You use 2 equivalents of KOH. Usually you have to heat it. If I forgot the little heat thing in one of the old exams, trust me, you heated it, and you'll make an alkyne. Right? So this basically is just working like doing 2 dehydrohalogenations like we did to make an alkene, right? You could say, hey, here's an alpha carbon, here's a beta carbon. My first equivalent of KOH, as it goes into my arrow, makes go that way. Makes a vinyl halide, right? Now my second equivalent, right? So someone in the first class would be to draw this out. So here's my KOH, grabs a hydrogen, electrons come down, push electrons up. That gets us to our vinyl halide. And my KOH, my second equivalent, is going to come in, grab this hydrogen, electrons are going to come down and push off the bromine. So I need to use 2 equivalents of KOH because I have to pull 2 hydrogens off my molecule. Another way we can do this is starting with a vinyl halide. Right, so we have a vinyl halide. Use sodium amide, and it does the same thing. It removes this hydrogen to make an alkyne. Now, if you're making a terminal alkyne this way, you have to add an extra reagent. You have to add water at the end. So you do the first part, the NaNH2, then you add water at the end, and that will make your terminal alkyne. So why does this happen? Why do I need to add the water? So I have my Na, and did I draw the same thing again? Right. So my amine can come grab a hydrogen, electrons come down, right? And I make my alkyne. plus I remake ammonia, right? The alkyne that I make, this is so that alkyne is more acidic than the alkene that I started the reaction with. So the next molecule of NaNH2 that's going to react, right? The next base that's going to react is going to react with the more acidic thing, right? So every time I make an alkyne, it reacts with NaNH2 before the starting alkene does. So this will grab a hydrogen off the end, and you end up putting a sodium on the end, plus making more ammonia. Right. So you don't want a negatively charged alkyne, right? You don't want to have sodium on the end of your alkyne. You've got to get rid of that somehow. So that's where the water comes in. This is a base, right? It can pull a hydrogen off of something. So if I take my alkyne and then I add water to it, it's going to grab the hydrogen off of water and it's going to make the terminal alkyne and hydroxide. Right. But because alkynes are more acidic than alkenes, right? We went over pKa's, right? The pKa of an alkene is somewhere around like 40. The pKa of an alkyne somewhere around 30, which means it's like, I don't know, 10 to the 10 times more acidic, like big number, because logarithmic and whatnot, right? So as soon as you make that alkyne, right, as soon as this alkyne happens, the base reacts with it. So you can never just like go from vinyl halide to terminal alkyne because the terminal alkyne is going to react. So you have to add that water as a second step to get your hydrogen back. If it's an internal alkyne, like we saw over here, right, you don't need, what the hell was that? There's like nothing there. Did I not put anything there? Did I stroke out that hard? Whew, man. Like I just feel like I blacked out for a second, right? You don't need to add water at the end because there's no hydrogen on the end of that alkyne to take off, right? You only have to add that water when you have the alkyne, when you have a terminal alkyne. Thing I want to point out real quick. Those two things are different, right? One of them will turn this alkyne into a trans double bond. One of them will do nothing. So make sure you don't confuse them when you like are looking at your reagents. One is NaNH2, and one is this or Na slash NH3, sodium with ammonia, as opposed to NaNH2. To make sure you don't confuse them, because people will confuse them a lot, and then like there'll just be a bad section on the test where they've just mixed up two reagents in their head and they just ruin their lives. I don't want that for you. I think that's where I want to stop. If you've been questioning if you should come to class, I have a bag of candy, and I'm going to practice reverse Halloween on Friday. I'm just going to throw candy at people. And I can throw candy at my computer screen, but then you can't eat it. So it doesn't work for you if you're on Zoom. But if you're here, I'll throw some candy at you. Reverse Halloween style. Anyone I hit in the head, 10 points for me. So keep your head on a swivel.